In this session, let us discuss about voltage comparators using op-amp. Here, voltage comparator means it compares the voltage at one of the input terminals of the op-amp against the voltage at the other input terminal and produces the output voltage depending on which of the input voltages is high. And normally the voltage comparators are open loop op-amp configurations, hence they produce plus or minus Vsat voltages at the output depending on the input difference voltages. The voltage comparator basically represented as shown in figure. Here the op-amp is in open loop configuration. V1 and V2 are input voltages, V0 is the output voltage. Therefore, V0 equal to AOL VID, where VID is V1 minus V2. AOL means open loop gain of the op-amp. If V1 is greater than V2, VID is positive. Therefore, V0 equal to AOL VID, that is plus Vsat. If V1 is less than V2, VID is negative, that implies V0 equal to minus Vsat. Therefore, V0 equal to plus Vsat for V1 greater than V2 and equal to minus Vsat for V1 less than V2 as shown in the transfer characteristic of the comparator. The main features of the comparator are: the comparator accepts the analog signals at the input but produces a binary signal, that is plus Vsat or minus Vsat levels at the output. The voltage comparator can provide a link between analog and digital systems. The next feature is the comparator characteristic is non-linear. It has two horizontal lines away from the origin. They are positioned at V0 equal to plus Vsat and V0 equal to minus Vsat as shown in figure. For the basic voltage comparator voltage transfer characteristic, we have at VID equal to 0, the voltage gain curve is vertical, that is voltage gain is infinity. But practically the voltage gain of the practical op-amp is of the order of 10 power 5, which is less than infinity. Therefore, at VID equal to 0, we will have not a vertical line but V0 rising linearly with VID. Even though this rising portion is very small, but it is not vertical, but it is linear over certain range of the input differential voltage VID. Transfer characteristic of the practical comparator is as shown in figure. Here at VID equal to 0 and above that value and below that value, the V0 rises linearly from minus Vsat to plus Vsat. Now let us discuss about different types of comparators. Classification of comparators: 1. Inverting comparator, 2. Non-inverting comparator. inverting comparator is as shown in the figure. It is a difference amplifier. V0 equal to AOL VID, that equal to AOL into V1 minus V2, where V1 equal to V reference, V2 equal to Vs. Therefore, V0 equal to AOL into V reference minus Vs. V1 is a DC signal, that is fixed amplitude signal, and acts as a reference voltage. V2 is a analog signal. As shown in figure 2, it gives plus V set when Vs is less than V reference and minus V set when Vs is greater than V reference. That is, output is 180 degrees phase shifted input. Let us discuss about this operation. If Vs is less than V reference, we have VID is positive. Therefore, V0 equal to plus AOL VID, that equal to plus V set. If Vs is greater than plus V reference, then VID is negative. That implies V0 equal to minus AOL VID, that equal to minus V set. Case 2. If Vi is the minus V reference, then V0 equal to AOL V1 minus V2 equal to AOL into minus V reference minus Vs. Here V0 equal to plus V set for Vs less than minus V reference and V0 equal to minus V set for Vs greater than minus V reference as shown in figure. So, in the inverting comparator, whenever input signal crosses the V reference voltage, then the output voltage will be at minus V set, and whenever the input voltage becomes less than V reference, the output voltage will be at plus V set. Okay. Now, let us consider non-inverting comparator. Here, the signal source will be connected to the non-inverting terminal and reference voltage will be connected to the inverting terminal. Now, whenever the signal voltage rises above the reference voltage, which is DC, we will get plus V set at the output, and whenever this signal voltage reduces below the reference voltage, we will get minus V set. Let us discuss about its operation. The non-inverting comparator circuit diagram is as shown in figure. The signal source Vs is connected to the non-inverting terminal and reference voltage V reference is connected to the inverting terminal. Here V1 equal to plus Vs, V2 equal to plus V reference. Therefore, VID equal to V1 minus V2 equal to Vs minus V reference. If VID is greater than 0, we will get V0 equal to plus V set. If VID is less than 0, we will get V0 equal to minus V set. That is, if Vs is greater than V reference, V0 equal to plus V set, and if Vs is less than V reference, V0 equal to minus V set as shown in figure. If V1 equal to minus V reference, then we will get the waveforms as shown in figure. Here, if Vs is greater than minus V reference, we will get V0 equal to plus V set. If Vs is less than V reference, we will get V0 equal to minus V set. Now, let us discuss about few applications of the voltage comparators. Let us start with threshold level detector. The threshold level detector is just an inverting comparator. Here, input signal Vs is as shown in figure 2a, and the reference voltage is nothing but the threshold level here in this circuit. So, whenever the input signal Vs is greater than that threshold level, we will get minus V set, and whenever that Vs crosses and becomes less than Vt, we will get plus V set, and it is as shown in figure. So, whatever may be the shape of the input signal wave shape, will get the output only a square wave. Another application of voltage comparator is zero crossing detector. Here the reference voltage is 0. So, whenever the input signal becomes more than 0 volts, then the output voltage becomes minus Vset in the inverting comparator mode, and when the input signal becomes less than 0 volts, then output voltage will be at plus Vset, and hence this circuit diagram is also known as sine to square wave converter. The circuit diagram of zero crossing detector is as shown in figure. Here the diodes D1 and D2 protect the op amp from damage due to excessive input voltage Vs. Because of these diodes, the difference input voltage VID of the op amp is clamped to either plus 0.7 volts or minus 0.7 volts. Hence, the diodes are also called as clamp diodes. If the op amp has built-in input protection, then the input diodes D1 and D2 are not necessary. The R compensation, R comp equal to R, is used to reduce the offset problems due to input bias currents. Here VID equal to V1 minus V2, that equal to 0 minus Vs, since V reference equal to 0. Therefore, if VID is greater than 0, that is Vs less than 0, we will get V naught equal to plus Vsat, and when Vs greater than 0, we will get V naught equal to minus Vsat. The output voltage amplitudes switch between levels plus or minus Vsat. Its output can be limited to the other voltage levels using voltage limiter circuit as shown in figure. Here two GNR diodes D1 and D2 are used. If VZ1 that equal to VZ2 equal to Vz, here VZ1 and VZ2 are GNR breakdown voltages of GNR diodes D1 and D2 respectively, and if V gamma 1 equal to V gamma 2 equal to V gamma equal to 0.7 volts, that is cut-in voltage of the silicon diode, we will get V naught containing symmetrical amplitude levels as shown in figure. It has got one drawback. If the input is a slowly changing waveform, that is very low frequency signal, Vs takes more time to cross 0 level, then V naught may not switch quickly from one saturation level to the other. Because of the noise at the op amp's input terminals, V naught may fluctuate between saturation voltages plus Vsat and minus Vsat, detecting 0 reference crossings for noise voltages as well as Vs. This problem can be cured with the use of regenerative or positive feedback that causes the output V naught to change faster and eliminate any false output transitions due to noise signals at the input. Now let us take up a special voltage comparator, that is Schmitt Trigger. Here in the Schmitt Trigger circuit we use positive feedback, and this Schmitt Trigger circuit is also known as regenerative circuit. The Schmitt Trigger, which is also known as regenerative comparator, is shown in the circuit diagram 1. It consists of resistors R1 and R2 which are connected from output terminal to the non-inverting terminal. So, the voltage across R1 acts as reference voltage at the non-inverting terminal. The reference voltage here is mentioned as threshold voltage level Vt. As in figure 1, the threshold voltages are obtained by using the voltage dividers R1, R2. The voltage across R1, that is Vt, equal to R1 by R1 plus R2 into V naught. that equal to beta V naught, where beta is the feedback factor given by beta equal to R1 by R1 plus R2. If V naught equal to plus Vsat, the voltage across R1 is called upper trigger potential UTP or upper threshold voltage, and it is represented by Vu, that equal to R1 by R1 plus R2 into plus Vsat, that is Vu equal to plus beta Vsat. If V naught equal to minus Vsat, then the voltage across R1 is called lower trigger potential LTP and is represented by VL equal to R1 by R1 plus R2 into minus Vsat, that equal to minus beta Vsat. As in figure 1, the input Vs triggers or changes the state of the output V naught every time it exceeds the certain voltage levels called Vu and VL, as shown in figure B and C. In figure B, the input signal voltage is given, and in figure C, the output voltage is given. As in figure B and C, we can say that whenever the input voltage is more than Vu, the output changes from plus Vsat to minus Vsat, and when Vs becomes less than minus VL, then we will get the output voltage changing from minus Vsat to plus Vsat. Thus, if the threshold voltages Vu and VL are made larger than the input noise voltages, the positive feedback will avoid the fast output transitions, which is a drawback in the zero crossing detector. In this Schmitt Trigger circuit, we come across the hysteresis action. Let us explain it. The closed loop gain of the amplifier with positive feedback is given by AV equal to AOL by 1 minus AOL beta, where mod AOL beta is the loop gain and beta is the feedback factor. If the loop gain mod AOL beta is adjusted such that 1 minus AOL beta equal to 0, the closed loop gain AL becomes infinite. Such an idealized saturation results in an abrupt transition, that is 0 rise time, between the extreme values of the output voltage. If the loop gain is more than unity, the output waveform continues to be virtually discontinuous at the comparison voltage. However, the circuit now exhibits hysteresis. This is also called backlash. The output of the comparator switches between plus Vsat to minus Vsat when the input voltage exceeds Vu and reverts back to its original state plus Vsat when input voltage goes below VL, as shown in figure 2. The hysteresis width is given by Vh equal to Vu minus VL, that equal to beta times Vsat minus of minus Vsat. If positive and negative saturation levels are equal, then the hysteresis width Vh equal to 2 beta Vsat. When Vh equal to 0, the circuit acts as an inverting zero crossing detector. The trigger levels Vu and VL both can be shifted to positive voltages so that they are symmetric around certain positive voltage rather than 0 voltage. This is achieved by adding plus VL to non-inverting input terminal, as shown in figure. The Schmitt Trigger finds applications in relaxation oscillators, and it is also used to eliminate the comparator chatter. Here the term chatter indicates the bouncing of the output voltage level in between plus Vsat and minus Vsat due to the DC or AC noise present in the slowly varying input signal. Now let us discuss about multivibrators. Multivibrators are also called regenerative circuits. They are classified into three categories: bistable multivibrators, monostable multivibrators and astable multivibrators. Bistable multivibrator. It is also called as flip-flop. It has two stable states. The bistable multivibrator has two stable states. Initially, it is in one of the stable states. Whenever a trigger pulse is applied, it changes from this initial stable state to the other stable state, and it remains in that stable state until another trigger pulse is applied. So, the bistable multivibrator requires two trigger pulses. Monostable multivibrator. It is also called as monoshot. It has only one stable state. It generates a single pulse of fixed duration in response to each external trigger signal. The monostable multivibrator is initially in stable state. When a trigger pulse is applied, it changes from this stable state to the quasi-stable state. There it remains for a fixed time duration, and then without applying the trigger pulse, it comes back to the initial stable state. So, it generates a pulse for each trigger pulse. It requires only one pulse to generate a fixed duration pulse at the output. Hence, the monostable multivibrator is also called a pulse generator. Astable multivibrator. It is also known as square wave generator or free running multivibrator. The circuit has two quasi-stable states. External trigger pulse is not required. The astable multivibrator will be initially in one of the quasi-stable states, and when power supply is on, it changes from this initial quasi-stable state to the other quasi-stable state, and it remains in that state for a fixed duration and comes back to the other quasi-stable state, that is initial quasi-stable state, and it once again remains in that initial quasi-stable state for a fixed duration, and once again it comes back to the other quasi-stable state. In this way, without applying any input trigger pulse, it changes from one quasi-stable state to the other quasi-stable state. The amounts of the time periods for the on and off time periods of the square wave generated at the astable multivibrator are fixed, and they are as per the design of the astable multivibrator. Now let us discuss about the astable multivibrator operation. The circuit diagram of astable multivibrator is as shown in figure. Assume that initial charge on the capacitor is 0, that is V2 equal to 0 when supplies are applied at t equal to 0. At this same time instant, V1 is not equal to 0. A very small finite voltage exists due to output offset voltage VOT, which is fed back through the voltage divider R1 R2. Although small, V1 drives the op amp into saturation. For example, let us consider the output offset voltage is positive. Since initial voltage on the capacitor is 0, it acts as short circuit. Therefore, voltage gain AV becomes 1 plus R by JXC equal to infinity, and this infinite gain leads to op amp saturation, which results in V0 equal to plus Vsat. With V0 equal to plus Vsat, we get V1 equal to R1 V0 by R1 plus R2, that equal to R1 by R1 plus R2 into plus Vsat. V2 rises because the capacitor C starts charging to V0 equal to plus Vsat through R. Let at t equal to T1, V2 is slightly more than V1. The comparator senses it and changes the output to minus Vsat as shown in figure. Now, with V0 equal to minus Vsat, V1 equal to R1 by R1 plus R2 into minus Vsat. V0 remains at minus Vsat until the capacitor discharges and then recharges to a voltage slightly more than minus V1. Let this occurs at t equal to T2. So, at t equal to T2, VID is positive and the op amp output is plus Vsat as shown in figure. Now, the cycle repeats indefinitely without the help of external trigger pulses and produces a square wave output voltage as shown in figure. The cycle period t equal to T2. It starts at t equal to 0 and ends at t equal to T2. Now, let us derive the cycle time period. The total cycle time period t is given by t equal to T1 plus T2, where T1 is the charging time period of the capacitor and T2 is the discharging time period of the capacitor. The capacitor voltage changes as per the equation Vc equal to V final minus V initial minus V final into exponential of plus T by Rc. Now, let us consider charging state. Here V final equal to plus Vsat, V initial equal to minus V1. Therefore, Vc equal to plus Vsat minus of plus Vsat minus V1 into exponential of plus T by Rc. At t equal to T1, Vc equal to minus V1. Therefore, minus V1 minus Vsat equal to minus of plus Vsat minus V1 into exponential of plus T1 by Rc. After simplification, we will get T1 equal to Rc ln of Vsat plus V1 by Vsat minus V1. Discharging state, V final equal to minus Vsat, V initial equal to plus V1. Therefore, the capacitor discharging voltage is given by the expression Vc equal to minus Vsat minus of V1 plus Vsat into exponential of T minus T1 by Rc. When t equal to T1 plus T2, Vc equal to minus V1, we will get the capacitor discharging voltage is as Vc equal to minus V1 equal to minus Vsat minus of Vsat plus V1 into exponential of T2 by Rc, which results into T2 equal to Rc ln of Vsat by plus V1 by Vsat minus V1. Therefore, T1 equal to T2 equal to Rc ln of Vsat plus V1 by Vsat minus V1. Therefore, the total time period t equal to T1 plus T2 equal to 2 Rc ln of Vsat plus V1 by Vsat minus V1. Here V1 equal to R1 by R1 plus R2 into Vsat when V0 is plus Vsat. Substituting this expression in total time period expression, we will get t equal to 2 Rc ln of 2 R1 plus R2 by R2. Therefore, t equal to 2 Rc ln of 1 plus 2 R1 by R2, and its frequency of oscillation is nothing but 1 by t. Therefore, frequency of oscillation f0 equal to 1 by 2 Rc ln of 1 plus 2 R1 by R2. In this session, we discussed about different types of voltage comparators and the applications of voltage comparators. We considered a special voltage comparator, that is a Schmitt trigger, and here we defined hysteresis also. and in this same session we discussed about multivibrators and we started the topic Astable Multivibrator, and we derived the time period expression and frequency of oscillation expression for the Astable Multivibrator. We will discuss about the remaining multivibrators in the next session.